Hi there. We are now at chapter 11, which is analysis of variance, better known as ANOVA. And for this chapter, for chapter 11 and ANOVA, you will need two tables. So I would have your textbook ready or um, definitely have them printed for the final exam. But at the back of the textbook, um, in the appendix, specifically for the F distribution table, you will need the F distribution table, which is A.3. And then you will also need the studentized range statistic table, which is A4, A.4. So these are two new tables that you'll be using for analysis of variance. So let's talk about analysis of variance and get you familiar with this. This is probably going to be the most challenging inferential test that you'll learn over the course of the semester. Some key um, uh, tips for success is to stay organized, take very good notes, and learn the notations. That's really key because there's going to be a lot of new notations with this one. So, analysis of variance, or the F test, also known as the F ratio, tests the differences between more than two conditions. You can actually test two conditions with analysis of variance, but typically we see it when we have more than two conditions. So the t-test, which you just learned, was limited to two conditions. So with the independent t-test, you had two independent conditions. With the paired samples t-test, you had um, two conditions with the same participants in each condition. And then even with the one sample t-test, you are comparing one sample to the population mean. So there were two means involved in that. And so t-tests were very limited to just two means or two conditions, whereas the ANOVA offers a lot more flexibility and is useful because we can have more than two conditions with that um, hypothesis test. So here's kind of how this looks. So with ANOVA, often there isn't always a true independent variable, or and there might be more than one independent variable with ANOVA. So they have created these terms to kind of help so that we're not having to distinguish between independent variable and quasi-independent variable and those types of things. So they use the term called factor, and that basically is that variable that designates the groups that are being compared. So if you look at this, there's um, the factor is program affiliation. So technically, there's only one quasi-independent variable, and that's which program affiliation there is. You could actually have two more factors, or two factors. Like, for example, it could be program affiliation related to gender. So, but we're not looking at that in this one, but that's why factor is there, is because you could have more than one independent variable or more than one factor. And then the levels are the conditions that make up that factor. For example, Jeff, Mary, Sydney, and Kathy are in the no program affiliation. Tim, Julie, Chris, and Tina are in the tutoring program. Sharon, Buddy, Lisa, and Cole are in the mentoring program. So those are the levels that they are within, but all of them are being um, evaluated on student success. So that's the dependent variable that stays the same for all of those. So this is what an analysis of variance would look like. And it could be more than three. There could definitely be five, six, seven. But I'm giving you the example of three in this case. So here's how we kind of tell what type of ANOVA to use. So if you're having to distinguish between a one-way ANOVA or a two-way ANOVA, a one-way ANOVA is with one factor, meaning one independent variable or one quasi-independent variable. For that last one, it was the program affiliation. That was one quasi-independent variable. In a two-way ANOVA, there's two factors being tested. So that's where it would be maybe we're going to look at program affiliation and maybe age or gender. And we're going to look at those two quasi-independent variables. So you won't learn how to calculate a two-way ANOVA. You're only going to have to worry about a one-way ANOVA. But I like to introduce that so you understand why suddenly they come up with this new term factor and levels in that because um, it, there are other types of ANOVA that needs to distinguish between. So with the ANOVA, there's also another kind of way to decide whether it's a one-way ANOVA. Basically, whether it's a between subjects ANOVA or a within subjects ANOVA is what we need to determine. If it's the between subjects design, that means it's a one-way between subjects ANOVA, and that means there's different participants in each condition, just like with the independent t-test, but now it's three or more conditions. Within subjects design is similar to the paired samples t-test. The same participants are in each condition, or it could be a matched subjects design where they're matched on different characteristics or traits. You are only going to learn the one way between subjects ANOVA. So when I just say ANOVA from this point forward, you should know that I am referring to the one way between subjects ANOVA. You're not learning the other ones. So I'm just going to use the term ANOVA, and you'll know that I mean one way between subjects ANOVA is what you're going to be worried about at this point. So when we are conducting the ANOVA, we need to make sure that we're meeting those assumptions just like we did in the other tests. And I'm sorry, this says four. There are actually technically four, but we're only going to cover three. We're going to really worry about the three main assumptions that you can have control over. ANOVA, with ANOVA, you need to meet normality. So either you have a sample size of larger than 30, and that means 30 in each condition. That's really hard to do. Or if the population that you sampled from is normal, you know that you met normality. So that normally distributed population. Independence of observations. So the probabilities of each outcome in the study are independent of one another, or they have equal weight. So no one person is impacting the outcome of another person, and no one person has a score that is weighted heavier than the others. So they're independent observations. And then homogeneity of variance, just like with the independent t-tests, the definition always says the variances are equal. Is what we really want is them to not be significantly different, is what we want. And you would test that just like you would with the independent t-test. But we're not going to worry too much about homogeneity of variance. You have enough to worry about with just calculating the one-way ANOVA. But you do need to know that that is an assumption that needs to be met. You do not want the variances to be significantly different from one another. And with the three, and like if you have three different conditions, you would still be looking at the largest variance versus the smallest variance. You don't want the larger variance to be twice as big as the smallest variance. So that's really how homogeneity of variance is evaluated. So, like I said, you're going to learn a lot of new notations for analysis of variance. This is a good time for you if you have not embraced like index cards or some way of memorizing the notations and what they're for. This is the time you need to, because analysis of variance has a lot of new notations, and some of the notations are repetitive, things that you've had in the past, but they mean something different with analysis of variance. For example, capital N, as you can see, it is the total number of scores in the entire study. So the number of participants that participated in the entire study, rather than the population size. So it's a little bit same notation, but means something different with ANOVA. And now you have a lowercase k, that's the number of treatment conditions or the number of groups. the lowercase n designates the specific number of people in a specific group, the number of subjects in a specific group. So that K, typically it distinguishes which group they're in. So it's usually done with numbers. Sometimes you can do it with letters, but it's usually numbers. So like N of 1 would be sample size for group 1. Then there's the degrees of freedom, BG, which is degrees of freedom between groups. And we can calculate that degrees of freedom between groups with K minus 1. So the number of conditions minus 1. And you'll be looking at degrees of freedom error, which is the degrees of freedom within the conditions. And you'll see numerator and denominator, and I'll clarify that as we get to that. Let's just think about the notations themselves right now. We calculate the degrees of freedom error with that capital N minus K. So the total number of participants minus the number of conditions. And so I'll show you how that's calculated. You're going to learn what the sums of square total is, the sums of square error, the sums of square between groups, and what mean square is. It's basically ANOVA's term for variance is what it is. So variance and capital MS are technically equivalent. It's just ANOVA has a different term for them. So these are just some of those notations that you're going to be learning that are new for you. So let's look at ANOVA overall. And now with the t-test, you are looking at mean differences. With ANOVA, because we have more than 2 conditions, we are no longer looking at mean differences because, for example, if you have one group, that their mean is like 5, the other group, their mean is 2, and then the other group is 5 again. Basically, you can't subtract all those, they'll flush each other out. And so we have to find another way to find the mean differences. So is what ANOVA uses is variance. And if you even think about the term ANOVA, analysis of variance. So it's comparing the variances, and it's computed using the variance between groups divided by the variance within groups, so the variance error. So as you can see, here's our actual equation for the F statistic. The mean square between groups divided by the mean square error. So same thing as saying the variance between groups divided by the variance within groups. So those are it's really what that means. Now there's a long way to get to this. So I just wanted to give you the overall equation right now, and then we'll start going through the steps and how this looks as we go through an example. So let me click forward here. Here we go. So here's an example of a research scenario. So this is a one-way between subjects ANOVA. So they're examining the driving performance under 3 cell phone conditions. 5 participants drive with no cell phone, 5 participants while talking on a hands-free phone, and 5 participants talking on a handheld phone. So there are 5 different participants in each group, each condition. So this is an example of a one-way between subjects ANOVA. So let's start breaking down how those notations work. So as you can see, you have group 1 is no cell phone, group 2 is the handheld cell phone, group 3 is the hands-free cell phone. So there's 3 conditions, or 3 groups as we call it. So K is the number of groups or treatment conditions. So in this case, K would equal 3. 3 conditions. Now the factor in this is just cell phone condition or cell phone usage, because it's kind of that overall term, but there's 3 conditions or 3 levels within that factor. So now we have that N of K, if you notice, and the K usually gets replaced with a designation of which group that sample size is for. So the number of people or participants in that sample. So if we have 5 people who participated in the no cell phone group, and we're calling that group 1, it's N subtext 1 equals 5. Same with the handheld cell phone group, N subtext 2 equals 5, and subtext 3 equals 5. So you can see they're equal sample sizes. You can actually have unequal sample sizes with a one-way ANOVA. I will never give you unequal sample sizes with a one-way ANOVA. I'm going to try to make your life simple and keep these as equal sample sizes because there's a whole different calculation for unequal sample sizes. Is what I want you to learn is more of like how does this work overall and get the skills good enough to understand how to analyze a one-way ANOVA. If you ever come across where you have unequal sample sizes, you can always use the software. There's software out there to analyze that. So here now we have that capital N, right? The total number of scores in the entire study. You can obtain that by counting all of the participants, all of the scores, how many scores in the entire study, or if you know how many is in each group, multiply if it's equal sample size, multiply the number in each group times K. So lowercase n times K if it's equal sample sizes. So we have 5 in each of these conditions. There's 3 conditions. 3 times 5 is 15. So if it's equal sample sizes, it's easy just to multiply the number of conditions times how many are in each condition to get that capital N, the total number of participants in the entire study or scores in the entire study. So here is an example of the basic calculations that we are going to need just to begin calculating ANOVA. So this is just getting you prepared to understand why it's so important to be organized, why it's so important to know your notations and what they stand for, because there's a lot of little calculations. And I always, always, always suggest you create some kind of a legend to distinguish between which condition and which notation numbers go to, because it's very easy to grab the wrong numbers because some of these numbers we're going to be using in multiple equations. You don't want to grab the wrong number accidentally. So as you can see, we need the sample size for each group. We need the sum of X for each group. So for like, let's hear sum of X for group 1 is if we went 4 plus 3 plus 6 plus 3 plus 4, that equals 20. Sum of X for group 2 is that 0 plus 1 plus 3 plus 1 plus 0, so et cetera, et cetera. And then the mean for group 1, so 20 divided by 5 is 4. Mean for group 2, 5 divided by 5 is 1. Mean for group 3, again, 5 divided by 5 is a mean of 1. You'll also need your sum of X squared for each group. So basically this 86, the sum of X squared, it's 4 squared plus 3 squared plus 6 squared plus 3 squared plus 4 squared, and that would equal 86. Just like the sum of X squared for group 2 is 0 squared plus 1 squared plus 3 squared plus 1 squared plus 0 squared. So you square each number individually, then add them. And so you need that for each group. And then you will need your sums of square for each group. And by now you should know how to calculate sums of squares. So the sum of X squared minus the sum of X total squared over the sample size, that equals the sums of square. So in this case, it would be, for group 1, it'd be 86 minus 20 squared divided by 5. And that would give us a sums of square of 6. And so you have to do that for each group. You have your capital N, which is 15. So if you look, there's 5 in each group. 5 times 3 is 15. Now, there's a couple of new ones here. If you see, there's sum of X subtext T. This is just adding up all 3 of the sum of X's. So 20 plus 5 plus 5 is how we get this sum of X T. And then this sum of X squared total is these sums of X squared all added together. So basically, adding all of these, 86 plus 11 plus 9 is our sum of X squared total, whereas the sum of X total is adding all 3 of these sum of X's together, okay? So hopefully that helps kind of give you an idea because you're going to need those for calculations as well. So just to give you an idea, and this is where organization is really key and making sure you have the notation straight with the calculations. The thing about statistics at this level, you don't have to be a math wizard to do well in this class. Really, in this class, it's you need to practice and you need to stay organized. Those are the keys to success in this class. So let's start from the beginning. Just as we have for all of our other hypothesis tests, the first thing we do is state our hypothesis. You really only need to state your alternative hypothesis now. So in this case, we're going to put there will be at least one mean difference among driving performance for driving with no cell phone, talking with a hands-free device, or talking on a handheld cell phone. So this gives us the conditions as well as the dependent variable for the overall study. So driving performance is our dependent variable. Now with the overall ANOVA, there could be any differences anywhere. There could be that all the means are different from each other, or just one mean is different from the others, or several means are different. It just depends. So ANOVA tests, is there any difference anywhere? It doesn't test like necessarily the means, it tests variance. So if there is a difference, a major difference in the mean variances, then is what happens is we move on and we do further testing, and we're going to talk about that. So we really want to look at the mean differences, but we can't look at the means alone and just subtract them like we did before because they'll flush each other out. We have to look at the variances instead. So here again, I've put my research scenario there. Let me move my head again. So here's that example research scenario so that we know what's happening, 5 in each. If we want to set the criteria, is what we need to do is take the degrees of freedom between groups, so that K minus 1, for this case 3 minus 1, because there's 3 cell phone conditions, minus 1, which is 2, and our degrees of freedom error. So degrees of freedom between group is K minus 1. Degrees of freedom error is that capital N minus K. So in this case, there's 15 participants minus 3 equals 12. So our degrees of freedom of error is 12. Now, the one big mistake I see students make the most is right here, accidentally putting 2 in there, like the degrees of freedom instead of actually K. Be sure that you're putting K and not the degrees of freedom. 15 minus 3, not 15 minus 2. Then you're going to go to the back of your textbook or to that table, that F distribution table. And if you'll notice, when you look at the table at the very top, it says degrees of freedom numerator. The numerator is basically, as you can see, K minus 1 is the numerator. This N minus K is the denominator. So this is our degrees of freedom between group. This is our degrees of freedom error right here. So it's set up that way in that F distribution table. So degrees of freedom for the numerator, which is between groups, is 2. So you'd find column 2, and then you're going to go at the far left and find the degrees of freedom error, which is 12. And then you're going to use 0.05. And so if you look at, line them up, degrees of freedom for between groups of 2 and 12 for the error, you should get 3.89. Now, the 3.89 is a light face. That's for 0.05. If it's bolded, that's 0.01. So we would use 3.89. Now with ANOVA, it's always positive. ANOVA is always positive because analysis of variance. And remember, variance is the average squared distance that scores deviate from the mean. The notation even has the squared. So if you're squaring things, they're always going to be positive. So the obtained test statistic is always positive for ANOVA, as well as the critical value for ANOVA. now we have our critical value, which is 3.89. Let's go to the next step. So the nice thing about ANOVA is it has this, what is called an ANOVA table. And I feel like the ANOVA table helps because is what it does is it helps us to remember the order of like dividing things and subtracting things, those types of things. And we can easily just use the table rather than memorizing equations. If you can memorize the table, you're doing pretty good. Sorry, I have a dry throat. So the ANOVA table always goes in this order. So you have your source, which is like the source of variance, basically. The first call or row is between groups. The second row is error, the within groups. The third is always the total. So the only things that you're really ever filling out is these other areas. And so you'll fill out the degrees of freedom for each. So we know that our degrees of freedom between groups is 2 because k minus 1, we got 2 already. The error, if you remember, it was n minus k. There was 15 minus 3. It was 12. So we could fill that in. And then the total is the capital N minus 1. So 15 minus 1. And we'll put that down here. That's 14. If you notice, 12 plus 2 is 14. So if you don't get 14 by 12 plus 2, you probably accidentally put the degrees of freedom in that k, where k should be. So it's a way for you to tell if you're doing some additions that are wrong. So let's go to the next thing. We're going to talk about, we won't go to the mean squares until we get the sums of squares. We can't calculate mean squares until we get the sums of squares of things. So we need to calculate these first. Then when we get those, we can calculate our mean squares and then calculate our F statistic right here. So again, here's our calculations that we had before, like the previous calculations where we calculated how many were in each sample, the sum of x for each group, the mean for each group, the sum of x squared for each group, the sums of square for each group, and et cetera, et cetera. So the first thing that I usually do is the sums of squares total. So is what I do is this here. This is what we're going to be calculating right now, is the sums of square total first, because is what we want to do is check if this between group sums of square plus the between groups error doesn't add up to this. We know we've done something wrong. And that's why I love ANOVA so much, because you can use the table to check your work. So is what you're going to do is you're basically doing a sums of square on the entire study, not just one sample, but the entire study. So if you'll notice, to get our sums of square total, let me find my pen. Okay, there we go. Sorry, I'm doing some scribbles. We're going to take our sum of x squared total, and it's going to be plugged in right here. That sum of x total comes from right here. And our n is the total number of participants, which comes right here. It is really the same equation as you've had before for sums of squares, but now we're using the total study altogether. So 106 minus 30 squared divided by 15, which ends up being 46, is our sums of squares total. And then we can plug that in to our ANOVA table. So basically, if I was to come here, I could put right here 46. So I know that whatever I get for between groups, whatever I get for error, I can plug it in. I could add those together and they should equal 46. So the next is our within group sums of square or error, or sums of square error. All we want to do is add all of our sums of squares together. We had 3 conditions, so we're going to add those 3 conditions. So we already have those. Sums of square 1 plus sums of square 2 plus sums of square 4 is our sums of squares error. So 6 plus 6 plus 4 is 16. makes our life simple. And then we could go back and plug that into our ANOVA table, and I'll get there. We'll do that. Then we need to go to our between groups sums of squares. So let me go real quick. This within groups or the error 16, that would be right here. I'll put that here. So this was what we calculated. Then we're going to go to the between groups is what we're going to do. So the between groups error or between groups sums of square is basically it. This is the most different calculation that you're going to have because you're not used to using means. So is what you're going to do is the actual equation for this is right here. Sample size times sums of square of the means. That's the actual equation. Now, this calculation can only be used for equal sample sizes. So again, like I told you, I'm only going to give you equal sample sizes. So this, a lot of times is what happens is students calculate the sums of square means, and they assume that's the sums of square between group. But if you'll notice, here's the notation, here's the equation, is what we do we have to calculate the sums of square means first. And this is the calculation. So it's basically our, we're going to just use the means and use those as if they're raw scores and calculate the sums of squares. So I'm going to put here SSM equals the sum of the means squared minus the sum of the means total squared divided by K, K being the number of conditions. So for this first part here, as you'll notice, here's our mean for group 1. It's 4 squared plus 1 squared plus 1 squared added together. And if you'll notice, we get that. And so 4 squared, 16, 17, 18, right? That's 18. So you could see that represented here. Then we're going to add some of our means. So 4 plus 1 plus 1. So 4, 5, 6, right? 6 squared is 36 divided by 3, right, is 12. So then it's 18 minus 12, and that's 6. So the sums of square means is 6. But the sums of square means needs to be plugged in right here. And you need to multiply that by how many are in each of the samples because they're equal. So there's 5 people in each of the samples. So 5 times 6 is 30. So you can check your work now. You go to your table and you look at, okay, does the sums of square total minus the sums of square equal the between groups or vice versa? So let's look at that table. So our sums of square between groups is 30. Probably the biggest mistake I see students make is reporting just 6. So you calculate the sums of square means and forget to multiply by the sample size. That's the biggest error. So very, very important that you multiply it by the sample size. So it should be a real red flag if you accidentally, let's go back, if you accidentally put in the number 6, like right here, 6 plus 16 doesn't equal 46, but 30 plus 16 equals 46. So that's how you can check your work. The nice part about this table is once you have these 2 columns filled in, everything is simple. So I always think of it this way. Put a division symbol here, 30 divided by 2 equals 15, and that's our mean square for between groups. Again, a division symbol here, 16 divided by 12 is 1.33. Oops, sorry. It is 1.33. So that's our mean square for error. Then to get our F statistic, just take this column and divide the between groups by the error. So 15 divided by 1.33 equals 11.28. It's easier if you have it all done right. You don't have to memorize all the equations, just some of them, and it'll just kind of flow for you. So our F statistic is 11.28 for this analysis of variance. So we do need to calculate an effect size still. And that's why we need that sums of square total, because that's part of calculating the effect size. So we use eta squared, which is still the percentage of variance or the proportion of variance in the dependent variable that can be accounted for by the treatment conditions. And it's typically what's reported for ANOVA, and it is the sums of square between treatments or between groups divided by the sums of square total. So if we look, our between groups or between treatments is 30. Our total is 46. 30 divided by 46 is 0.652. That's our eta squared. So basically saying 65.2% of the driving performance can be accounted for by the cell phone conditions. That's a pretty large percentage in reality. So let's go back really quick. If you remember our F obtained, if you recall, we looked at our critical value, and our critical value, let's kind of look at it this way. I'm going to go back real quick because I think it was 3.89, but I don't want to give you, 3.89. I don't want to give you the wrong number. Our critical value is 3.89. So it's always going to be in that positive, 3.89. And we're going to look at, okay, where does our F obtained fall? Well, F obtained is 11.28. It falls way over here. So this test is significant. So there is a significant difference somewhere. Doesn't tell us where, it just tells us there is a significant difference somewhere in between those cell phone conditions. So because it's significant, we need to do post hoc tests. So whenever there is a significant ANOVA, we need to conduct post hoc tests to just tell where the means are significantly different. So the overall ANOVA, the F test tells us somewhere there's significance. The post hoc tells us where specifically things are significant. So this is a statistical procedure that tells us exactly which groups are significantly different from which groups. And so whenever there's a more than two conditions, we need to run post hoc tests. So this kind of gives you the map. So you conduct your overall ANOVA. If you reject the null hypothesis, meaning their significance, you conduct post hoc tests. If you conduct an ANOVA and you retain the null hypothesis, meaning there's no significance, you stop, and that means there is no significant difference between any, and you don't conduct post hoc tests. So you stop and you don't conduct post hoc if the overall test is not significant. That's an error that I see students making a lot, is conducting post hoc tests no matter what. And the reality is you shouldn't be conducting post hoc tests if it's not significant. It's even scarier when I see students get post hoc tests and they say there's significance there, but the overall wasn't significant. You shouldn't be getting significance either way. Something has gone wrong. So this is where you need that second table. So we're going to use Tukey HSD for our post hoc test, specifically because we're using equal sample sizes. And Tukey HSD is the only test that I will teach you that actually is for equal sample sizes. So Sheffy is for unequal sample sizes. Tukey is used for equal sample sizes. And so to be able to find, it's called the HSD. It's basically a critical value is what it is that you're going to compare things to. You're going to look at the Q, which is that critical value in the studentized range statistic table. So Q is using the degrees of freedom error and the degrees of freedom and range, not degrees of freedom, but the range. And when they say range with ANOVA, it just means the number of conditions. So range and K mean the same thing. I don't know why they don't keep it simple, but that is the unfortunate situation with ANOVA, as the terms fluctuate back and forth. So the studentized range statistic is a whole separate table. It's table A.4. And you'll see at the top it says range. And so for us, the range is 3 because K is 3. And then you're going to use your degrees of freedom error. If you remember, that was 12. So on the far left, degrees of freedom error is 12. And because we used 0.05, we're going to use the light face. So 3.01 or 3.78, because we're going to use 12 and 3, and we're using the light face. So our critical value for this, which is Q, is 3.78. So as you can see, we plug in 3.78 right here. And then it's the mean square error. So if you go back to your table, you're using this mean square error is what you're using, 1.33, and you're dividing by sample size. So remember, because it's equal sample sizes, that number's the same for each of those conditions. So 5. Take the square root of that. And this square root of 1.33 divided by 5 times 3.78, you get 1.95. And is what you're doing is you're looking to see which mean difference is greater than 1.95 is what you're doing. So that you're going to compare all of the possible combinations of the mean differences and see which ones are greater than 1.95. So I'll show you what that looks like. So if you recall, for condition 1, the no phone, the mean was 4. For condition 2, the handheld, the mean was 1. For condition 3, the mean was 1. So all we want to do is look at all the combinations. So group 1 versus group 2. It's 4 minus 1. That difference is 3. That is greater than 1.95. So we know that condition 1 versus group 2 is significantly different. And then group 1 versus group 3, 4 minus 1. The difference is 3. So that again is greater than 1.95. So we know that is a significant difference. And then if we look at group 2 versus group 3, 1 minus 1 is 0. That's not significantly different. So we just know, okay, now it's group 1 versus group 2 and group 1 versus group 3. Is what you need to do is kind of look and see what this makes sense. So no phone has better driving performance than handheld or hands-free. It's significantly better. So that's how you kind of figure out where the significant differences are. So here's how we would report the results for ANOVA. It's very important that ANOVA results are reported appropriately. If this overall analysis was not significant, we would not have used or included the second sentence. It would have just been the first sentence. But because it is significant, we're going to say analysis of variance revealed there is a significant difference in driving performance related to cell phone condition as F, and these are the degrees of freedom that you use to look up your critical value, and it's always the degrees of freedom between groups, comma, degrees of freedom error, 2, 12. So remember, numerator, denominator. Equals, and that's your test statistic, 11.28. We know that P is less than alpha because it was significant. And again, we don't need to tell one-tailed test because it's automatically a one-tailed test with ANOVA. And with eta squared 0.65, period. That's the overall ANOVA that you just tested. But because it's significant, now we need to talk about where it's significant according to Tukey post hoc tests. So as you can see, Tukey post hoc tests show that driving with no cell phone showed significantly better driving performance than driving with a hands-free device or driving with a handheld cell phone. So here's how the overall APA results are reported with ANOVA. It's lengthy when you get significance, and it's definitely extra lengthy if there's more than 3 conditions. But I'm making your life easy by having equal sample sizes across those conditions. So you only have to worry about dealing with Tukey post hoc tests alone. So ANOVA is affected by the same things as t-tests as far as power. Remember, power is the probability of rejecting a false null. basically you're finding significance when there really is significance. It's not an error. So as sample size increases, the power increases. So as the n increases, the power increases. As the real effect increases, um, it'll increase. So basically, is what we mean by the real effect is the means differences, the mean 1 minus mean 2, like when we're doing that post hoc test, as those mean differences increase, or that larger overall magnitude of the test increases, the power will increase. But unfortunately, as variance increases or variability increases, the power decreases. So that can be a problem as well. In addition, that it doesn't, it, I didn't include on this, alpha, as alpha increases, power increases. So if you use a 0.05, that is going to be more powerful than using an alpha 0.01. So even that alpha level is going to impact power. As you increase that alpha, power is going to increase. So hopefully this helps. I know this is a tough one, and it might take you a little bit of time to really learn this. I do have another supplemental video that I will put in this week's overview that just goes through just a hypothesis test. I recommend watching that and go through and take your Chapter 11 lecture quiz. Hope you were able to retain some of this. Please don't hesitate to reach out with questions if you need them.